This section explains how synthetic biology was engineered into existence by a structural transplant. The move takes the abstraction hierarchy of electronics, where standard compose into gene circuits and devices compose into circuits, and maps it onto DNA, where promoters, ribosome binding sites, coding sequences, and terminators, where promoters, ribosome binding sites, coding sequence units, and transcription units compose into gene circuits. The primitive that does the work here is not the parts list. It is what licenses composition at all, a common signal carrier whose flux is a current. Electrons flowing through a wire, quantified in amperes, become RNA polymerases and ribosomes flowing through DNA, and messenger RNA, quantified as POP-S and RIPS, quantified as POP-S and RIPS. The chapter opens the book's wager that circuits must be model-driven, designed in silico before any wet lab work, while conceding that biology has no electromagnetism yet. This section explains the single structural move that founds synthetic biology. Synthetic biology rests on one structural transport, the abstraction hierarchy of electronics, where components compose into devices and devices compose into circuits carried wholesale onto DNA. The step that does the work is whatever licenses composability. Parts snap together because they share one conserved flux, and the composability comes from that shared carrier rather than from any geometric fit of the pieces. RNA polymerase and the ribosome are the electrons, and their throughput is the current, measured as POPs and RIPS. Everything the book will build is this one mapping elaborated. The promoter, RBS, CDS, terminator transcription unit, and the pools that store free carriers like biobatteries are the same single mapping worked out again. And it runs under a standing demand. Every circuit wears a mathematical model before it touches a living cell. This section explains what it means to choose a kinetics. A model is the map from concentrations now to concentrations later. It is predictive, or it is not a model at all. The cartoon of who talks to whom does not qualify. The falling stone anchor holds exactly where its no friction anchor holds exactly where its no friction assumption does, and nowhere else. Once the species and reactions are fixed, one choice closes the system into ordinary differential equations. That choice is the kinetics, the law-binding interaction to rate. That single choice forks the whole enterprise. Mass action reconstructs every collision mechanistically. Hill functions merely fit the observed pattern from two measurable parameters. Mechanism versus phenomenology, fidelity traded against tractability. The chapter's title is its thesis. Modeling is choosing a kinetics. Everything downstream is that one commitment made explicit. This part explains what a model is at the level of what it computes, and how you build one. A model is defined by what it does. What it does is predict how species concentrations move through time, where a cartoon only names who touches whom. The whole move of the chapter is that the prediction lives inside its assumptions. Take the falling stone. The formula S equals 1/2 gt squared is exact for a falling stone and wrong for a paper sheet. Yet the model is not broken. The no friction premise simply failed. Building a model means choosing a kinetics, the rule that turns a fixed set of species and reactions into ordinary differential equations. Two choices frame everything after. Mass action is mechanistic, reconstructing molecular collisions from the bottom up. Hill functions are phenomenological, fitting observed activation and repression curves. Pick the kinetics, get the dynamics. This section explains how the computer enters the modeling work. Ordinary differential equations describe a gene circuit's dynamics, but even four-coupled species resist closed-form solution, so the derivation from Chapter 2 gets handed, unchanged, to a numerical solver. That is the whole move of this chapter. The model is re-entered and executed at the machine, carried over from the InGALYSYS. COPA-C reads the same 7 reactions and the same rate constants and integrates them forward until steady state. The roughly 44 monomers and roughly 193 dimers you computed by hand reappear on screen. The structure that carries this chapter is a confirmation loop. The machine validates the analysis rather than standing in for it. Everything downstream inherits this posture. The stochastic runs, the parameter scans, the stability checks, pencil proposes, solver checks. This section explains what to do when the equations exist, but the closed form does not. You keep the model intact and change only the solver. Chapter 2 handed you the differential equations of a gene circuit. Most such systems resist solution on paper, so this chapter integrates them numerically instead, through COPA-C. The move is generic. A differential equation is a rule for the next instant, and numerical integration merely steps that rule forward, trading the exact trajectory for a computed one to arbitrary tolerance. The proof that it works is recovery. Rerun Chapter 2's dimerization circuit and the same steady state falls out, approximately 44 monomers and 193 dimers. Analytics validates numerics where both can reach. Numerics extends where analytics cannot follow. That boundary is the one this chapter is built to cross. This section explains why the deterministic equations of Chapter 2 are only an approximation and what sits underneath them. The deterministic ordinary differential equation of Chapter 2 is the large number limit of something deeper rather than the truth itself. A continuous concentration is what a discrete count of molecules looks like once the count is huge and the fluctuations average away. This chapter installs the layer beneath that limit. A gene circuit is a small population of discrete molecules whose reactions fire at random instants, so its trajectory is a probability distribution rather than a smooth curve. Carry this. Determinism is stochasticity with the noise integrated out, valid only when the species are plentiful. When a circuit runs on a handful of molecules, the discreteness itself steers the outcome. Only simulating the random walk of the counts recovers that behavior. Solving the equations does not. This section explains why a chapter on stochastic gene circuits needs to exist at all. A deterministic model is the large population limit of a stochastic one. Chapter 2's smooth equations are what you get when molecule counts run high enough that fluctuations average out. This chapter's whole thesis is the finite n correction. Noise scales like 1 over the square root of n. So when a gene circuit runs on a handful of molecules, the mean stops being the story, and the fluctuation becomes the signal. The random walk anchor carries it. A molecule stepping left or right drifts nowhere on average, yet spreads as the square root of n. That is the generative move. When the countable units are few, replace the trajectory with the probability over trajectories. Gillespie simulation is that replacement paid for in compute. This section explains how to tell whether a steady state is stable. A steady state is where production and decay cancel. Stability asks something. The balance itself cannot answer. Does a small nudge decay or grow? Think of a pen. Lying horizontal and standing vertical are both rest states, yet one survives a push and one topples. The verdict is local and spectral. You linearize the flow around the fixed point, collects the first derivatives into the Jacobian, and the sign of the real part of its eigenvalues decides everything. A negative real part pulls you back. A positive real part expels you. The imaginary part only sets the oscillation. Existence and fate are separate facts. This is the universal move wherever a fixed point's destiny is asked. Linearize and read the spectrum. This section explains how to read a circuit's fate near a steady state without ever running the numerical integrator. Until now, the circuit's fate was whatever the numerical integrator happened to draw. This chapter extracts the fate without the trajectory. A steady state is where production balances decay, where f of the steady state equals 0, and the only question that matters is whether a small nudge decays back or runs away. Here is the generative move. Linearize at the fixed point, Taylor expand, and discard everything past first order. The local dynamics then collapse to a single relation. The rate of change of the small displacement equals the Jacobian times that displacement. The behavior is governed entirely by the eigenvalues of the Jacobian. The sign of the real part of each eigenvalue decides. Negative pulls back, positive flees. The imaginary parts spin. A pen lying flat on the table versus a pen balanced upright is the whole idea. This is the critical point, primitive. Fate near equilibrium is read off the spectrum of the derivative. This section shows that the two circuits founding synthetic biology are one analysis read at two settings. Both were born in January 2000, and the move of this chapter is to see what look like two separate inventions as two regimes of a single stability analysis. The toggle switch holds memory. It has two stable states, and its parameter path shows hysteresis. The jump up and the jump down happen at different thresholds. The repressilator instead ticks, a sustained oscillation. The eigenvalues from Chapter 5 predict both. A real eigenvalue crossing 0 folds one steady state into a coexisting pair, which is bistability. A complex pair crossing the imaginary axis, the Hopf bifurcation, spawns a limit cycle. Here is the surprise. Topology fixes neither fate. Cooperativity and feedback strength do. The behavior is a bifurcation. Selected regime. Read off from where a parameter crosses. This part explains why the behavior of a synthetic gene circuit lives in geometry rather than in chemistry. Function is topology. Whether a circuit remembers or ticks is not written in its molecules. It is written in the shape of its steady-state set, in the intersections of the nullclines in phase space. Chapter 6 extends. Chapter 5 stability analysis to the two founding circuits of the field. The first is the toggle switch, whose two coexisting stable states give hysteresis and hence cellular memory. The second is the repressilator, where a stable fixed point loses stability and births a limit cycle, a Hopf bifurcation yielding sustained oscillation, a Hopf. Here is the lesson that generalizes. Tune a parameter past a threshold and the phase portrait changes kind, not degree. Memory and clock are the same equations under different bifurcations. Nonlinearity, cooperativity, a Hill coefficient n greater than 1 is what licenses the multiplicity. This section explains why the same toggle switch gives two different answers depending on how you compute it. One circuit, two computational substrates, two different answers that carries the whole chapter. Chapter 6 handed you the toggle switch. Here, it becomes a probe of how you compute a model rather than of what the model contains. Integrate the ODE, and both repressors settle symmetrically. Run the discrete stochastic algorithm at high repressor promoter affinity, and one promoter falls silent for long stretches, breaking the symmetry that the mean field law forbids. The deterministic answer is only the large number limit. When molecules are few, the fluctuation stops being noise around the truth and becomes the truth itself. Stability is then read straight off the eigenvalues of the Jacobian. All real and all negative means the state holds. Bistability needs cooperativity to exist at all. This section explains why a deterministic and a stochastic simulation of the same circuit are genuinely different objects. The two diverge precisely where the biology gets interesting. They are not two roads to one answer. Chapter 7 makes the toggle switch the demonstration. Solve its ordinary differential equations, and you track a mean that, under bistability, is a state the cell never actually occupies. Run. Gillespie on the identical reactions and single trajectories fall into one. Well or the other. Flipping when repressor promoter affinity is high and molecule counts are low. Here is the primitive to carry forward. The ordinary differential equation is the low noise limit of the master equation. It is faithful only when copy numbers are large and the landscape is single-welled. Elsewhere, the average lies. This part explains rule-based modeling and why it refuses to enumerate. Consider a repressor bearing a DNA site, a dimerization site, and a chemical site. It already spawns more molecular species than you can enumerate by hand, because the reaction list explodes combinatorially. Rule-based modeling refuses that enumeration. You specify the intention, molecules as agents with named sites, each site's possible states, and rules that rewrite sites locally when molecules interact. Then software, BioNetGen, unfolds the extension, every species in every reaction, mechanically. A rule is a pattern match. The rule that selects R with its binding site B in the unbound state picks out every repressor detached from DNA, whatever its other sites are doing. So one rule subsumes a whole reaction class. The chapter derives mechanistic, repressilator, and toggle switch models this way. The grammar generates the language. This section explains how Chapter 8 escapes the explosion of biochemical state. Put n operators on a promoter, and you get 2 to the nth power distinct species. The state space explodes faster than any hand can enumerate it. Chapter 8's move is to stop writing down states in 407 species, and 407 read down the generators instead. You declare the molecule types together with their functional sites, you declare the rules as local changes to those sites, and you let BioNetGen unfold the full reaction network. For a 4-input logic evaluator that no one could derive by hand, that unfolding yields. The primitive here is Solomonov, directional. The model becomes the shortest program that generates the mechanism, rather than the mechanism written out term by term. Every earlier chapter derived its circuits by hand because they were small enough to allow it. This one is the tool for when they are not. This section explains how a gene circuit becomes a schematic you can compose. A gene circuit stops being an undifferentiated bag of reacting molecules and becomes a schematic. It is made of DNA parts and pools of signal carriers, and each part carries a fixed ordinary differential equation model behind typed interfaces called terminals. Wire 2 matching terminals together, and you compose not just the drawing, but the mathematics. The whole circuit model falls out of the composition of its parts models, and all you do afterward is tune parameters. What makes this work is a shared currency across every interface. On one side, there are fluxes of signal carriers, the biological currents. On the other, there are free concentrations, the biological potentials. This is the exact electrical analogy, current and voltage at every node. Composition is free, precisely because the interface is conserved. Marquesios. Parts and pools is that discipline made runnable. This section explains what makes a genetic circuit designable. A genetic circuit becomes designable the instant its parts compose the way electronic components do. You wire them together, and the whole circuit model assembles itself out of the component models with no re-derivation. That is the chapter's single move. The parts and pools framework makes this literal. Promoters, ribosome binding sites, and pools of RNA polymerase each carry a pre-built ordinary differential equation model plus terminals, interfaces that exchange one common currency. That currency has two forms: fluxes of signal carriers, which act as biological currents, and free molecule concentrations, which act as biological currents, and free molecule concentrations, which act as biological potential. Match the terminals, and composition just works. The tool called Promoti sums the pieces into an SBML model for the simulator, COPASI, to run. The primitive doing all the work here is compositionality through a shared interface. It is the same reason Kirchhoff's laws are enough to design a radio, without ever reaching down to Maxwell's equations. This section explains what parameter analysis is and why its output is a curve rather than a number. A model is a map from parameter space to behavior, and parameter analysis reads that map one axis at a time. You freeze every kinetic constant but one, sweep that one across decades, and watch a steady state, observable trace its response curve. The chapter's anchor is the K1 scan. You vary the polymerase II promoter binding rate and follow the active promoter concentration as it climbs toward its ceiling. The payload is the shape of that curve, where it is steep, where it plateaus, where the system stops caring. Past a K1 of roughly 3 times 10 to the 7th power, the active promoter level barely moves, which means the parameter has left the regime that governs the circuit. This is a one-dimensional section through a high-dimensional surface, a partial derivative made visible. This section walks through how to work with a synthetic circuit model that carries more rate constants than you can measure. The chapter is the grammar for living with that ignorance, 3 moves on one problem. Fitting turns the unknown parameters into the minimum of an objective function. When the landscape is rugged, stochastic search, methods like simulated annealing and genetic algorithms tunnels toward the global optimum instead of stalling in a local one. Reduction exploits timescale separation, so fast reactions collapse into algebraic relations. This deletes the parameters and the stiff, ordinary differential equations you couldn't pin down anyway. Sensitivity then ranks which parameters even matter. Robustness delivers the real surprise. Some behaviors, like bacterial exact adaptation, are structural, invariant under every rate, constant. What survives the parameters is precisely what you never had to measure. This section covers how every design question about a circuit reduces to one operation. That operation probes the map from kinetic parameters to steady state. COPASI runs that probe 4 ways. Sensitivity reads the local derivative of that map, which parameter nudges which species, and how hard. Robustness sweeps one parameter across an interval and watches the steady state drift. Optimization and fitting invert the map. They search parameter space for values that minimize an objective. Fitting is just optimization, whose objective is distance to data. The leakage constants mark the boundary the chapter is built on. They read near zero under sensitivity, yet turn catastrophic once K1, LK reaches 1% of K1. The local slope tells you nothing about the global landscape. This section explains how one idea ties together every analysis technique in the chapter. A simulated circuit is a function from kinetic parameters to steady state, and every technique here reads that one function from a different direction. Sensitivity is its local derivative, how each parameter nudges each concentration. Robustness is just asking over what range that derivative stays small. Optimization inverts the function. You hold the output you want fixed, say R2 equal to 2 times R1, and search parameter space for a preimage. So it is one map. Read through 3 queries: the forward slope, the inverse toward a goal, and the inverse toward data, with Copazy as the mere executor. Prior chapters built the forward model. This chapter runs it backward, and it picks a deliberately fragile, leaky toggle switch so the analysis has something to catch. This section explains what a circuit motif is, and why a handful of them generate every behavior in the chapter. A motif is a wiring pattern whose topology fixes its dynamics. The circuit is what it does. A handful of transcription units in a particular configuration deterministically yields one behavior class, and the sign of the loop is the reading key. Negative feedback accelerates the response and clamps concentration, which gives you homeostasis. Positive feedback slows the response and splits it into 2 stable states, which gives you bistability and memory. Close the loop with net. Negative interactions, and you get oscillation instead of a set point. Everything else in the chapter, the feed-forward pulse generators, the Boolean gates, the cascades, the cell consortia, is the same move at higher arity. The generative primitive is this: read function off topology, then compose motifs to build arbitrary circuits. This section explains what a motif is, and why its wiring, not its molecules, decides what it does. A motif is a topology to function map, a small, recurring wiring pattern of transcription units whose structure alone fixes what it computes. One regulated promoter suffices. Negative feedback sharpens response and holds homeostasis. Positive feedback slows it, and with cooperative binding, splits the system into 2 stable states, which is memory. The chapter's single move is that function is a property of connection. Swap the molecules, keep the wiring, keep the behavior. Boolean gates, cell consortia, dividing labor across a population, re-engineered signaling pathways, all the same kind of object. Complex circuits are then compositions of these blocks, exactly the design pattern stance, a small, closed vocabulary that generates the large space.